in terms of everything that this code does, sorry. Yeah, because in terms of everything it does, it's just opening the model, running it, and training it. And the only customization really was this weight initializer, which is running 0 in Xavier. And in terms of parameters, this is exactly what was in the paper, which was SGD, momentum, weight decay, etc. So no matter what the weird reports we had on data loading, etc., it seems to be fine. In terms of the other parts of the homework, those are pretty straightforward. The flatten module just flattens things. That's pretty much all it does. The all CNN module is just a big old sequential. Hopefully you guys all figured out these parameters correctly. You should have been able to reverse engineer them even if you couldn't figure it out from the paper. But roughly speaking, those are your modules. And in terms of the actual pre-processing steps, I think things like the 0 mean, whatever, that just means make things 0 mean, so you subtracted these. I think pretty much everyone got to their 100%, so you probably all got the answers correct, but the question and the reason to reread the homework, even if you got 100%, is to understand, like, oh, did I do it efficiently, or things along those lines. So really, you should see that most of these functions are like one line plus a bunch of documentation. And that's really all it takes, and not a lot of weird looping or anything to get what you need to get. Yeah, that is understandable. A lot of people were confused about ZCA, but we kind of posted the formulas, and you guys can go from there. Yeah, that was probably the one trickier part. But basically, this is the covariance matrix, and then a little debiasing of the covariance matrix, and then we're just getting the eigen, which technically we could use like eigenvalue decomposition here, but whatever. So yeah, I think actually Beck gave some nice discussion of it on Piazza, but there are also some good visuals. I'm curious if that's there. There might be a nice image of what ZCA whitening does. Something along those lines. But heightening, sharpening, etc. Things still look like what they're supposed to look like, but things are normalized and things have a nice little variance. So it tends to make things learn a little faster. We'll quickly go through part 2, and I think we'll do a little bit of at least homework 3, part 1. So this is the concatenated utterance model on part 2. And I think this is actually where people had a lot of questions, and it's definitely worth reading through how this thing works, because this is the one where I was getting like sub-minute epochs, and people are getting like 20 minutes. And that just goes to show how much of a difference training and the efficiency of like doing one-hots and doing multiplications really factors in. So what's important to know about here is this is the concatenated utterance model. In general, if you have a bunch of stuff that is different lengths and you need to put them into a rectangle, you only really have 2 choices. One choice is to pad things out into a rectangle and have each thing along one dimension with a bunch of zeros where they don't line up. The other choice is to concatenate things together into one long list. If you concatenate everything together, that does mean you're being more space efficient, but in terms of your processing, it can be a little trickier sometimes. Doesn't always work out that you have the choice between the 2 of them, but it's always worth keeping in mind that those are, like, for example, when you run packed sequence in Python, your packed sequence is transforming your padded array into concatenating everything in just the parts that you need. And as a result, the shape is that particular shape. So it becomes 2D instead of 3D when you pack. Anyways, so the first function here is the assignment vector, which is just, we've got our bounds, and I'm turning the bounds into a list of when things are on or when things are off. So my assignments table is the list of however many frames we have, and then a subsection of the assignments from the beginning to the end is going to be set to I. So this is going to look like a bunch of zeros and a bunch of ones and a bunch of twos and a bunch of threes, whatever. It's just the integer values of where each vector, or where each frame is supposed to be assigned, which phoneme it belongs to. And then in terms of the data set is just pulling everything from NumPy, and then it's wrapping everything into a torch tensor. So I've got torch tensors already. That's just a nice, makes things a lot cleaner going forward. So then when you implement get item, you're just getting an item from a list that's already tensors that are already in torch. So you don't need to from NumPy each time or anything. That's a pretty fast one, but even so, it's nice to not have to worry. Probably the bigger part, which is where I think a lot of people got confused, was in the collation function and how that all goes together. So they're kind of two sections. The first section is where I am figuring out how many frames and how many phonemes. So the total number of frames is going to start off with padding times 2 times how many things are in my batch. And that's because each phoneme, or sorry, each utterance gets padding items before and padding items after. So for each utterance, there are 2 padding to begin with, plus 1 for each, plus adding up all the frame sizes. So the total number of frames I'm going to have in my concatenated utterance, which has padding in between utterances, is going to be my padding plus the length of the utterances. And then the total number of phonemes, those don't really pad or anything. That's just going to be the padding size 0. So this section here is calculating out how much space I'm going to need by going through the batch on a first pass. Then there's a section which is going to allocate all the memory that I need. The reason for this syntax is just to make it kind of dynamic. So this means that it's just going to use the data types of whatever it happens to see. But in terms of in your own code, I don't know if we have like Notepad up or something. But in terms of your own code, what we've been recommending different places. Float storage dot underscore new shared, and then you give it some size, and then dot new and some size. So that actually needs to be passed in twice. So this has been our kind of standard quick way of allocating your shared storage. So you see here, if use shared memory isn't enabled, it does the shared storage. Otherwise, it's just creating regular old new variables, or new tensors rather. So that's step 2 of collation. And the third part of collation is when I go through the batch and actually copy everything in. So I've got a pointer for where my frames start and a pointer for where I am in the phonemes. And then I'm basically just copying in each of the frames and each of the phonemes into that array. So this array is kind of one long array as opposed to the padded rectangular array, but it ends up being much more efficient for this particular assignment because you're not spending any time at all on the empty space in between. You're not really, there's a limited amount of padding and it's upper bounded. This particular function is worth noting, which is the function for how to make a one-hot off of assignments. Now the reason this one-hot function is written this way is because it can actually run on CUDA. So it's important to understand how you can actually run, generating one-hots on CUDA is very important because especially if you have a very large data set, generating the one-hot on your CPU means you're copying a ton of data over. So you're comparing copying one int versus if you got 30,000 things in your vocabulary, you would be copying over 30,000 floats, which would clearly be a lot more. So it's worth understanding. In terms of how it actually works, the length that I need to deal with is the maximum of the assignment. So that's just getting how wide does my one hot need to be. I'm creating a new floating point item, which I'm resizing out to that size, and I'm zeroing it. And then scatter operation is scattering into, it's taking the number one, I'm sorry, this is along dimension 1, use the assignments, and at those assignment points, assign them equal to 1. And also, right, so that's got a lot of 1s, and they each mean something different. But basically, this function here is the one that actually fills out the 1s in the one hot. And this function here is just dropping off one column of the one hot, because there's one column we don't care about, which is the padding dimension. So in our construction of the data set, we basically got one giant long list of all of the utterances concatenated together, and each frame has been assigned to either a phoneme or to padding. The paddings are removed. So we've got this one-hot assignment, and this one-hot assignment translates from the frames to phonemes. So it's frames by phonemes. When we take our frame predictions, we multiply it by this, it gives us phoneme predictions. So exactly what we want. Initializer, same as before, just kind of copied it over. The actual model, in terms of the layers we used, it was just a bunch of conv1ds. We didn't do anything special, really. The first one has input dim being 40. It's got the same hidden dimension, kernel size of 3, 1 padding, so everything's the same size. And then it just goes through 9 more, which are hidden to hidden, and then a final layer, which is hidden to output. So in terms of general structure, pretty straightforward. 1 conv-d goes in, then 9 conv-d is hidden, and then 1 conv-d goes out. They're all pretty much about the same size, except the last one was a kernel size of 1. Doesn't really make a huge difference, but this is the actual model part, which you guys should know how to toy with. The confusing part, I think, for most people was when we actually get to the summation. And the actual model, this is pretty much all you need for the concatenated utterance model that people were asking questions about for a very long time. So all you end up with is you've got your forward model. Your forward model here, this is just your, running CNNs, whatever. And then this is the important part, which is the pooling. So the pooling is making a one hot out of the assignments, and then matrix multiplication between your model outputs and the one hots will sum the one hot, will sum the logits. If we sum along the one hots, that gives us the sum of the assignments. So that's like a count of how many things were in each phoneme. Does it make sense to everyone? Hopefully that when you sum along the one hots, that's counting how many times each thing is being used. So that's going to be our numerator, or our denominator in the pooling function. So this is the average, and that average should make sense because it's the sum over the logits divided by the total sum over the assignments, which is how many phonemes there, or how many frames there are in each phoneme. And then after that division, just do a transpose to give it back in the right order. But really, that's the collated, or that's the concatenated utterance pooling model, and that ends up giving you very efficiently. Here's an epoch timer. Maybe worth spending a second to understand just callbacks. Callbacks are super useful. Every framework worth its salt has callbacks of some type, and that's the way that's preferred to actually modify and do things. So what this one does, all it really does is tell you how long epochs took, but basically it can start a timer when the beginning of epoch, and it can end a timer at the end of the epoch. And when you give this callback to Inferno, it will run it for you. Another time. Training should look very familiar by now. Some KWArgs. This line is very important if you want to get your code to run quickly. So make sure you have something like that. And of course, that's actually used here. So I brought that up several times. Still have questions. So keep the kW args in mind. Loaders, pretty straightforward. The trainer, similar things, although I did turn off size averaging here. Yeah, that's pretty much what we end up with. The default cross entropy loss just works with the concatenated utterance model as we have it, because basically the output of our model is logits for each phoneme and only for each phoneme. So this would be an example actually of the question you had earlier about what to do with padding and stuff. This is an example of a model where we just structure it so that the module output is only the parts that are not padding, and then it's not a problem. So there are many approaches in machine learning, and that's just one of them. Yeah, and then some code for writing predictions, CSV writer. If you guys have any questions about CSV writer, please ask, but there's plenty of Stack Overflow, et cetera, on that. Yeah, and then just writing out a CSV, argparse, et cetera. So that's our homework 2, part 2 little recap. I think we'll just do homework 3, part 1, because I know everyone's got that one taken care of at least. Solutions, PyTorch. Just cleaning up some code recently. Yeah, actually, I think homework 3, part 1's probably actually going to take a little while, because that's where a lot of the dropout was. You guys all remember homework 3, part 1, at least? Homework 3 is more familiar than part 2? Okay, then homework 2? Okay, great. Now, in terms of actual structure, this is my training file. My training script, what does it do? Right. So this is kind of the way you want to organize things in Python. It's important to understand why it's this way, which is this is a script. It's a script, which means it's really meant to be run from the command line. It's not meant to be part of a module that you distribute and give to people and other people use, and it's not it's not meant for that purpose. It's meant to run something. So we divide our code up between our modules, which provide functions that other people are going to use, and our scripts, which are just kind of like one-off type things. So this is a script. You could technically import it and do things, but you can't do relative imports. There's certain things you can't do in a script that you can only do in a module. And a lot of people were getting errors with their submissions because they weren't understanding the difference between scripts and modules in Python, which, to be fair, is a very kind of wishy-washy distinction. But basically, this calls from homework3.vanilla model, import this. What this is saying is look for a folder named homework3, look for a file named vanilla model in there, and then these functions should be both a part of that. So bring those in and then run them. But it's important to get your script code and what you actually run broken out, and then that gives you complete freedom to organize your code however you want. So we do have a lot of random files out here. I ended up putting everything that we need to go through for the class into one file, just so it's easier to give to you guys, but you really should be putting everything into a separate file. Best practice is like one class per file. Every function should be like 10 to 40 lines tops, like really trying to cut everything down into manageable chunks. So don't do what we do what we say, as people say. Okay. Anyways, in homework 3 vanilla model, I'm calling it vanilla model because this is none of the dropout regularization, anything. It just runs the baseline model. It's good enough to pass on Autolab. It's fine. And then I'll show you guys the one with a bunch of bells and whistles. It's a bunch more code. Data set, this is worth mentioning. So this means that it's implementing a class of data loader. It's a subclass of data loader. But I'm not calling the data loader constructor because it does a bunch of stuff that I don't want to do. I'm actually overriding the iter, which you normally don't do, but this is an iterator. What the __ iter is that's run when you call a for loop on, or try to iterate over something. So if you create a class, and that class has a iter function, and then you create an instance of that class, and then you iterate over that instance, this is what gets called. So if you have a for loop, the for loop calls this, even though you don't actually write that function name anywhere in your code. It's being called implicitly. So this is called once for each for loop. And really all it's doing is getting the word count, rounding it off to batch size, doing the reshapes, putting everything to long, putting everything into CUDA, and then in a while loop it yields. So this is 100% of the reshaping, batching, and everything that we've told you about on Piazza. It's funny, but it really is like 10 to 15 substantive lines of code or like 3,000 posts. It's just the way things work out. But in terms of simplicity, what's worth mentioning here is that I'm putting things onto CUDA because there's not a huge amount of data. It's integers, so the data is really dense, which means we can afford to put the whole thing onto the GPU. So everything's on the GPU, and all the data loader is doing is just taking some slices out of those tensors that are already there. It's going through an order, and that's the other reason I'm overriding iter. I'm overriding iter because I want to have the control to tell you what order everything's going to happen in my data set, and that's the easiest way to do it. Gumbel we've talked about before. Definitely read the paper. There are 2 papers that came out at the same date, basically, that both discovered Gumbel. It was one of those interesting situations where they like co-discovered it at the end of last year. Go figure. But anyways, so that's the Gumbel sampling. The model itself is relatively straightforward. It is embedding from vocab to 400, LSTM 400, 1150, 1150, 1150, 1150, 400, 400 vocab size. So you see how that makes a nice little palindrome, kind of. But you should appreciate the symmetry that this shows. And this is important to pay attention to because this will be a good starting point for things like homework 4, where you're doing very similar types of things. Here, I'm setting the bias data of the projection bias. If I pass it into the model, that's where my unigram logits are going to come in. So we'll talk about that later. And this part right here is the wait time. In terms of the actual code, it's really just running the embedding, running each of the RNNs. So you notice in this vanilla model, I'm not even worrying about the input hidden state carrying over or anything. So that's not even included. So that's why I'm not passing anything in to my RNN here. And then I run the projection layers. And then the rest is just the generation, which is basically the same as homework or as Recitation 6. But I can scroll back and go back to that if people have questions about the actual generation. Same epoch timer. This is a good example of how you can like override a module to do something else you want. So this is a new class, which is based off of this class. And the difference is the way that it views things. And it reshapes before calling the parent constructor. Smooth unigram model would also be worth. Please just ask questions if you guys. So see, we're running low on time, and we're not going to be able to cover all of the embedding dropouts and stuff, which are probably where people had the most issues. But I'll pull those up really quickly, maybe, and then let you guys go. But the real, that's probably the best part to make sure you guys understand are things like this. This is a custom dropout implementation, and that would be your efficient way to do dropout. You create a new item that's a shape that you want. You do a Bernoulli sample on the model, and then you need to multiply the inputs by that Bernoulli sample divided by 1 minus self.p. So a lot of people were doing things like forgetting this part of custom dropouts, and that completely throws off your results. But the reason I have this class, which is shaped dropout, is because I'm an engineer, and this is you wanted to be able to think about ways to create modules and reuse those modules. So this shaped dropout can be used to create the embedding dropout because you want to drop out a particular shape there. It can also be used for dropout 1D. I think we're actually at time, so even though it says 9:20 here. But we will pick up on homework 3 and the rest of homework 3, hopefully at a later recitation. and we'll let you guys know. But anyways, and I think TA hours today, we're going to try to do LTI Commons, which seems to have some good space. So, good luck, guys. Any homework 4 questions you want to shout out while you're here?
Just want to say this is really helpful to see you.
Yeah, like definitely spend your time looking through the recitation, through this code, run it against yours, see where the differences are, because like so many people got stuck on so many things on training the all CNN, and it's really just this. So if you can figure out where you went wrong, hopefully that'll help you in the future of whatever is going on. I guess I hit stop recording then.